Hi, welcome to the second module for the second video, and we will continue looking at permutations, and this time with restrictions. Often there are restrictions on how the objects are to be arranged. With this type of problems, we settle the restrictions first and apply the basic counting principle. Now, we briefly looked at this in module 1, and the same principle applies here. Always settle the restrictions first before you continue applying the counting principle. Let's examine this closer with an example. 4 boys and 5 girls are to form a line. In how many ways can this be done? Find also the number of permutations in which we will look at A to D in the next slides, but let's answer the first part here. In how many ways can this be done? This here referring to 4 boys and 5 girls. So this is 9 students in total. We have 9 students, and we want to permute these 9 students. Now we know how to do this. We draw a box with 9 columns, and 9 times 8 times 7, we know this is equals to 9 factorial. If you were to use your calculator and calculate this, you will get 362,880 ways. So this takes care of the first part of the question. Let's move on. Next, it says here the first 2 are girls. Now keep in mind here we have 5 girls. So let's draw the boxes here. We need to divide this into 9 parts. One more. Okay, here we go. Now it says that the first 2 are girls. So let's take care of the permissions or the restrictions first. So there are 5 ways to put the girl in the first row, and then we have 4 ways to put the girl in the next row. So this takes care of the restrictions. Now there are 7 available slots, so we can arrange the remaining 7 in 7 factorial. So to answer this question, how can we permute in such a way that the first 2 are girls? This is the same as 5 times 4 times 7 factorial. And this will give you an answer of 100,800. Now the other way of looking at this is also we can do it permute it in such a way that there are 5 girls, we want to permute 2, and then the remaining we will permute them in 7 factorial. Now this again will give you the same answer. So remember here, the key idea here is that you must take care of the restrictions first. Let's move on to the next part. The first is a boy and the last is a girl. Now again, if we were to draw the boxes, let's just take care of the first and the last one. We know that there are 7 slots in the middle here. So the first is a boy, so we can arrange this in 4 ways, and then right at the end it has to be a girl, so it's in 5 ways. Now the middle part here, the remaining 7, they can be arranged in 7 factorial. So once again, this is very similar to the A question, which is 4 times 7 factorial times 5, which yields the same answer as just now, 100,000 and 800 ways. Let's move to the next part. The boys are together. The boys are together. Now, this is a very interesting question, so please pay close attention here. We draw the boxes again. One, two, three, four, five, six, seven, eight. One more. We'll add it on this side. Okay, so the first four, let's assume here, the boys are together. So these boys, these four boys need to be together. Now, these boys among themselves, they can be rearranged in 4 factorial. Okay, so we can rearrange these boys. They are together, but they can be rearranged in such a way that it yields 4 factorial. Now, the remaining are all girls. Now, we know there are 5 girls remaining. 5 girls remaining. Now, we need to assume that this group of boys can be counted as one block. Okay, they are one block. The reason being here is that among themselves they can be rearranged in 4 factorial ways, but as a block they can also move in between the girls. Now, there are 5 remaining slots here. So 5 plus 1, if we consider this as one block, there are 6 ways that I can permute the 5 girls and the 1 block of boys. So this yields 6 factorial. Okay, let me repeat again. The key idea here is the boys themselves can be rearranged in 4 factorial ways, and then consider them as one block. And then you have 5 remaining blocks. So 5 plus 1 is 6 blocks, and these 6 blocks can be rearranged in 6 factorial ways. So the answer is 4 factorial multiplied by 6 factorial. And this will give an answer of 17,280. Now, this ensures that the boys are always together as they are being rearranged among the girls. Let's move on to the last part of this problem, which is no 2 girls stand next to each other. Now, how can we do this? Again, let's draw a box here. With 9 columns. And one more this side. This is 9. Now, according to this restriction, if the first one is a girl, the next one needs to be a boy, and a girl, and a boy, a girl, and a boy, a girl, and a boy, and a girl, and a boy. So we have a total of 4 boys and 5 girls. Okay, let's cancel this because this is 1 extra. So these are the 9 columns with 5 girls and 4 boys. Now, the girls can be permuted in their position, because there are 5 of them, in 5 factorial ways. How about the boys? The boys can be permuted in their locations in 4 factorial ways. What does that mean? Let me elaborate a little bit. That means this boy and this boy can change locations. This boy can also change locations with this boy or the other boy right here. That means just the arrangements of the boys there's a permutations of 4 factorial. And similarly for the girls, there's a permutations of 5 factorial. So when we multiply these two, we get that 2,880 ways. So again, the key to permutating with restrictions is take care of the restrictions first. Draw the boxes if needed to understand the logic of the problem before you do the calculation using permutation. So please go through this example again. This is a great example, by the way, just to put all the things that we have learned thus far together. So we just briefly looked at an example, a question, to understand further about permutations with restrictions. In our last video, we will look at 2 questions, 2 examples, just to bring everything together that we have learned thus far and to solve problems of permutations and permutations with restrictions. I'll see you in the next video.